So previously, in the previous module, we had covered variate distributions. Variate distributions, but in one dimension. In the previous module, we looked at variate distributions that were not joined. Variate distributions that were not joined. For example, we saw that the Poisson was a distribution that was discrete, and it was defined as exponential negative lambda power x over x factorial, and x was starting from x equals 0, 1, and so on. That was the Poisson. That was the Poisson distribution. Now, in this module, we don't look at one dimension. Why am I calling this one dimension? Because f of x is single valued. We evaluate x using one variable. We evaluate f using one variable, x. Now, for joint probability distribution, we look at f. But taking on two variables, x and y. Variables, x and y. For the previous module, we are looking at f in terms of a single variable. So here we have joint distribution, where a random variable x is jointly distributed with a random variable y. Still, in the previous module, we looked at the discrete and continuous probability distributions. So here for joint distribution, we are going to look at both joint discrete distribution and joint continuous. So what do we mean? Technically, if we start with joint discrete distribution, if x and y are discrete random variables, the function given by f, now you see, f takes on all the input are x, the variables are x and y. It's like we are operating in R2. So f of x and y is the probability of x equals x, y equals x for each pair. Now this is not for a single value, for each pair of variables x and y within the range of x and y, and that is what we call the joint probability function of x and y. So the function f of xy, which is given by probability of x equals x, comma y equals y, for each pair of variables x and y within the range of x and y is the joint probability function of x and y. Now, the same properties, we looked at properties of probability in one dimension. Remember, probability is non-negative, the total probability is 1. All those properties also apply here. You see, that joint probability function as defined above is non-negative. And also the total probability. The key issue here is that for one dimension, we are having, the property was saying that the sum of all x values, f of x is 1 for one dimension. That's what we saw. Now here for two dimension, there are two sums. Sum over all x values and also sum over all y values, because x is jointly distributed with variable y. Therefore, the law, the axiom for total probability to be equal to 1 transforms into this expression that is for a joint probability distribution. Then also property 3, property 1, non-negative, property 2, total probability is 1. Property 3, if a pair xy is not one of the possible pairs of the random variables, given that you have a pair of coordinates that do not form possible values of this pair, then the probability of that pair should be a 0, because it's not among the possibilities. It's not among the possibilities which the pair of random variables x and y can take on. Therefore, probability in that case is a 0. Then the last property for So this property considers a subset A of R2. For the pair XY, we are in R2. Now, for a particular subset A of the Cartesian plane R2, the probability of XY to be in that subset A is the same thing as obtaining the sum of the probabilities where the values or the pairs XY are taken from the subset A. Therefore, this is the introduction to the joint probability distribution. So we are going to go through this example. We are going to go through this example here and see how the joint discrete is applied. Kindly note down this example. Having looked at the properties, also note down those properties. So the example says that let X be, hope you've taken note of this preamble. Otherwise, maybe I recap it a little bit. I have said that in the previous module, we are looking at a random variable. We are looking at a random variable, for example, X, like the Poisson, it was in terms of X only, the binomial in terms of X only, exponential distribution in terms of X only. Now here, for the joint probability distribution, we have joint discrete and joint continuous. Just as the name sounds, joint, we consider two random variables jointly. X and Y are jointly distributed. That's why we do not have f of x, but we have f of xy. And f of xy, how is it defined? In the other module, f of x was defined as probability of x equals xc. Now here, f of xy is defined as probability of x equals x and y equals y, and it is for each pair. In the other module, we are considering for each value of x. Now this is for each pair, and that is what we call the joint probability distribution. And these are the properties. They are the same properties. What differs is that here we are operating in two dimensions. F is non-negative. We sum over all x. The total probability should be 1. If a pair is not among the possible pairs of the random variable, then its probability is 0. Then for a particular subset, the probability of x for a pair to be in set A, that is equivalent to summing over, that is equivalent to obtaining the probability, but when the pairs xy are taken from the subset A. So this is what I have defined. So we have this example. What does this example say? This example says that let x be a random variable. Let x be a random variable which takes on values 1, 2, and 3. Now you see, we have a random variable x and y be another random variable, bringing out the essence of joint. So it is x together with y, jointly distributed. So x is a random variable which takes values 1, 2, 3, and y is another random variable which takes values 1, 2, 3, and 4. And their joint probability function is specified in this table. So this table is also given. Kindly take note of this table. For this table, we have x. You see, I think now there's something I'm not putting right. Something I'm not putting right. This table is given. Yeah, that's how x and y are randomly distributed. So x, you see, x takes on values 1, 2, 3. Then y takes on values 1, 2, 3, 4. And they are jointly distributed, implying that now look at where I'm highlighting with black. You see where I'm highlighting with black, 0.1. Now for 0.1, that is for a pair. 1, 1. For a pair 1, 1, do you know what that means? That means f of 1, 1. And f of 1, 1 means probability of x equals 1, y equals 1. What have I said? Look at the 0.2. This 0.2, which I am highlighting here. You see, 0.2, up there is a 2, y equals 2, then down here there is a 3. So that is f of what is x? X is 3. Start with x, don't forget. X is 3, then y is 2. And that is the same thing as saying probability of x equals 3, y equals 2, and that value, colleagues, is 0.2. That's how the table is interpreted. If I'm here, are you seeing where I'm having a 0? Up there is a 4. Then horizontally here there is a 1. So we start with x. This is 0. I'm meaning this is 0 here. So for that case, x is a 1, so that is f of 1. We start with x, then y is 4. And that is the same thing as saying probability of x equals 1 and y equals 4. So this table is given. This is 0. This table is given. So what do they require us to obtain? They require us to obtain the following. So that's what the question requires us to find. Find the following. Given that table and how I have interpreted it, I don't know why I'm being disturbed, but this thing is misbehaving. Yeah, that's it. So that is the question which we are going to go through.